Inside this emergency department, a heart monitor generates a single piece of data, an IP packet stamped with the source address 192.168.2.14. Its destination is a secure server in the basement data center. But the moment it enters the network wire, it hits a wall of digital gridlock. It is caught in a broadcast storm. In a flat, undivided network, there are no walls or intersections. Every printer, tablet, and monitor transmits data to every device simultaneously. The background noise drowns out the actual signal. This gridlock also exposes a severe vulnerability. Without internal boundaries, a receptionist's tablet in administration has a direct, unobstructed line of sight to the highly restricted servers in the pharmacy. A single open floor plan breaks down under its own weight. To operate safely and efficiently at scale, the architecture requires physical-style boundaries built out of digital logic. To build those boundaries, we have to look at the address itself. This diagram shows a 32-bit IP address cleanly split into a network neighborhood and a host device. For years, rigid classes A, B, and C locked this dividing line at the 8, 16, or 24-bit marks. This caused massive logistical problems. A Class B assignment provides over 65,000 addresses, leaving most permanently wasted. But the step down, Class C, provides only 254 addresses, too small to contain the hospital's devices. The global supply of IP addresses was burning out on empty space. The network needed a way to break the rigid class rules. The hospital's IT architects draw up a blueprint to divide the building into 3 isolated zones: administration, emergency, and pharmacy. They execute this division using a subnet mask, a secondary sequence of numbers like 255.255.255.0. This mask acts as a precise filter, telling the routing hardware exactly which bits belong to the network and which belong to the host. Today, engineers write this using Classless interdomain routing, or CIDR notation. A label like /24 simply means the first 24 bits belong to the network. By changing that number, the boundary line can slide to any bit position, completely ignoring the old Class A, B, and C rules. This sliding scale provides the exact mathematical control required to custom fit a digital network to the physical layout of any building. Inside the router's processing core, that subnet mask is applied to every single piece of data at the speed of electricity. The hardware performs a bitwise AND operation. As this graphic illustrates, the router lines up the IP address and the subnet mask in raw binary. Where the mask has a 1, the router preserves the IP bit. Where the mask has a 0, it wipes the bit clean. The remaining sequence strips away the individual device identity entirely. What is left is 192.168.2.0, the true network address for the entire emergency department. To calculate exactly how many of these isolated departments can be built, engineers use the formula 2 to the power of n. Here, n is the number of bits borrowed from the host portion and given to the network portion. Every borrowed bit exactly doubles the number of available subnets. Conversely, the number of devices that can fit inside each subnet is calculated as 2 to the power of h minus 2, where h is the number of host bits remaining. We subtract 2 because the top and bottom addresses in any block are strictly reserved. The very first address acts as the network ID, and the very last is the broadcast IP, used to signal all local devices at once. Neither can ever be assigned to a computer. This microscopic bit borrowing is the exact mechanism that isolates traffic and creates secure, quiet digital rooms. Looking back at the hospital blueprint reveals a complication. Administration requires hundreds of connections, the emergency room needs 50, and the restricted pharmacy needs only 20. Assigning them equal /24 blocks would mean handing the pharmacy over 200 IP addresses that will never be used. The solution shown here is variable length subnet masking. By applying different subnet masks to different sections of the address block, engineers can carve the space into unequal pieces, a /26 for the emergency room and a /27 for the pharmacy. The addressing perfectly matches the device count, ensuring zero waste regardless of the department size. With the boundaries drawn, the broadcast storm clears. The heart monitor's packet now sits in a quiet, isolated emergency subnet, ready to transit. By design, this packet cannot simply cross into another subnet. It must be handed off to a Layer 3 router, which acts as a strict security checkpoint, verifying permissions before allowing the data to reach the basement servers. When zooming out to the global internet, this logic runs in reverse. As visualized here, internet service providers combine thousands of adjacent subnets back together into massive blocks with shorter CIDR prefixes. This process, called route summarization or supernetting, compresses routing tables so global data can flow at high speeds. Strict separation at the local level, paired with aggressive summarization at the global level, is what keeps the internet navigable. When a packet finally needs to leave the hospital entirely, it faces a hard stop at the edge of the building. The 192.168 address it carries is defined by RFC 1918 as a private IP. Private IPs are strictly banned from the public internet. Because they never leave the building, thousands of different organizations can safely use these exact same numbers internally without causing a collision. To cross the boundary, the edge router performs network address translation, or NAT. It strips off the private internal address and replaces it with a unique, globally registered public address. Subnetting dictates the internal layout of the organization, while NAT safely manages the exterior gateway to the outside world. The packet successfully clears the edge router and enters the public web. This level of organization does carry strict costs. Every single subnet boundary requires deep engineering complexity to design and maintain, and permanently sacrifices 2 IP addresses to network overhead. While technologies like VLANs achieve similar separation at the switching layer, subnetting specifically organizes the higher, routing layer of the stack. Without this system of sliding boundaries and bitwise math, the 4 billion available IPv4 addresses would have burned out decades ago in a gridlock of broadcast traffic. Subnetting is the foundational architecture that prevents the global internet from collapsing under its own weight.